When an industrial pump suddenly shudders and blows a thick cloud of steam across the plant floor, the physical breakdown is obvious, but what happens next often triggers a secondary, less visible breakdown in the system. Look at this work order submitted after the event. It reads, PM done, equipment issue, pump malfunction due to unexpected reasons. Imagine walking on to the next shift. How could you diagnose the root cause with these notes? This lack of clarity creates data chaos. Vague descriptions and fragmented terminology populate reports and dashboards, obscuring the physical reality of the asset. This forces teams to rely on diagnostic guesswork, treating every recurring failure as a brand new mystery. Over the next 5 minutes, we are going to fix this. We will walk step by step through the rules of data entry to transform this chaotic note into a golden record, using an approved terminology glossary and a structured classification library. Data entry functions as a core reliability practice. Each entry forms the evidence base used to improve equipment performance and guide future maintenance strategies. Let's look at how to build that evidence. Step 1 is categorizing the core issue. To do this, we open the primary work order screen to classify the failure. This is where we run into a common trap. When technicians type custom failure names like motor breakdown into an open free text field, identical issues end up recorded under a dozen different names. To prevent this, we skip the free text field entirely. Instead, we use the drop-down menu to select the standardized, approved term, in this case, engine failure. Next, we attach the corresponding classification code. We scroll through the approved code library and select MTR-F001. By locking in these structured codes, we establish a common language across the organization. This prevents data corruption and ensures that reliability engineers can run accurate Pareto analyses to identify recurring trends later on. Now we need to draft the problem statement. The goal here is technical precision. We only want to answer the what and the why, leaving out any unconfirmed speculation. Our original note stated, pump malfunction due to unexpected reasons with various outcomes. This is overly verbose while offering zero operational value. We will rewrite this to be specific. The new description reads, hydraulic pump P25B pressure drop from 3,000 psi to 2,200 psi due to seal wear, causing low flow. Notice the exact measurable parameters here. Documenting the drop from 3,000 psi to 2,200 psi provides a direct technical path for troubleshooting. This level of specificity eliminates diagnostic guesswork and directly reduces mean time to repair. The next shift can see exactly what changed, allowing them to pull the right tools before they even arrive at the machine. With the technical description written, we need to review our draft specifically to catch and remove unapproved abbreviations. In our original note, we see the abbreviation PM. While it might make sense to the person who wrote it, context degrades over time. To a new hire or an auditor, PM might mean preventative maintenance, or it could mean project manager. We consult the facility's approved glossary and rewrite the text to explicitly state preventative maintenance. Resolving this ambiguity guarantees the record remains readable and actionable for cross-functional groups, future reviewers, and new staff. Before finishing the draft, we run a completeness check. This step ensures we have captured the full context of the maintenance event. We start by verifying equipment identification. We check the record, confirming that the exact asset, the P101A pump, and the specific component, the SKF6203 bearing, are clearly listed. Next, we verify that the precise nature of the failure and the operating conditions at the time, in this case, high vibration operation, are documented. If a technician omits the bearing type or the operating state, the next crew has to figure it out from scratch, wasting time on repeated diagnostic efforts. When we include comprehensive details, like specific component IDs and failure modes, we preserve the exact context required for effective root cause analysis and accurate reliability modeling. The draft is complete, but we must pause for one final check before hitting submit. We need to validate our data against the current physical state of the equipment. If the engineering team recently executed a design change, like installing a new impeller, it might introduce a new failure mode that isn't captured by old codes. We review the asset configuration and confirm that the failure codes we assigned match the current design and are not referencing obsolete standards. With the details verified and aligned with the physical equipment, we finally submit the completed record into the system. Regularly validating data against management of change procedures prevents misleading historical analysis and preserves leadership's confidence in their key performance indicators. Let's compare our starting point with our final output. We replaced a chaotic, generic note with a clean, detailed golden record. The operational impacts happen immediately. Because the terminology is exact, planners save time scheduling follow-up work, and engineers have the clean data they need to run accurate performance analyses. Over the long term, entering maintenance data with this level of discipline creates a reliable knowledge base. It allows organizations to accurately anticipate equipment failures, optimize their resource allocation, and successfully execute predictive maintenance strategies. Every maintenance professional is a data steward. The quality of tomorrow's decisions depends on the quality of today's data. Apply these rules to every work order you touch, and download the quick reference summary to guide your next entry.